let's talk about oscilloscopes. What is an oscilloscope and what does it do? Well, oscilloscopes are very useful for us whenever we're trying to analyze or design alternating current circuits or any circuit that has voltages or currents in it that change over time. We know that whenever we're building a very basic DC circuit or a digital logic circuit, if we want to measure a voltage or a current at any place in the circuit at a particular moment in time, we can do that using a multimeter. A multimeter contains a voltmeter and an ammeter, which allow us to measure voltage and currents, respectively, in different places in our circuit. The problem with those is that they only measure voltages and currents at one particular instant in time. Whenever we have voltages or currents that change over time, then we can't use a multimeter because it's just showing us a tiny snapshot of what is happening in one maybe microsecond, where a microsecond later, our voltage or current might look a little bit different. So all an oscilloscope is a voltmeter or ammeter, most likely a voltmeter. It measures a voltage that takes in a bunch of voltage measurements really, really fast at a very high sampling rate, and then it plots those on a graph so we can see how the voltage or the current is changing over time. That speed at which an oscilloscope can measure a voltage is usually shown somewhere on the actual enclosure itself. This one, for instance, is rated at 5 gigasamples per second. So this is taking in 5 times 10 to the 9th samples of different voltages per second and plotting that on our screen to see. And that's really useful for us whenever we're, say, building an RC circuit, a resistor and capacitor network circuit, where it creates a voltage pulse whenever we send a DC voltage through it. And we can see exactly what that pulse looks like at different moments in time using the oscilloscope. So now let's get into how we can actually set this up to read and plot those voltages at different places in our circuit. So here's one of the oscilloscopes that we have here at the lab in Florida Poly. This is a Tektronix MDO3104, and this is actually a fairly high-end piece of equipment. Now, let's talk about what each one of these buttons does on this device, because there are a lot of buttons and different dials and knobs here, so it's very easy to feel like this is a really daunting machine to use. But I promise, once you get a little bit more familiar with all of the different buttons that are on here, that learning curve will not seem so steep at all. So the very first thing we have to do when we're going to use the oscilloscope is, of course, turn it on. You'll find the power button for these in the bottom left down here. Press that once and then give it a solid 30 seconds or so for the entire unit to power on. In the meantime, let's talk about leads or probes. There are a few different types of connectors that we can attach to the various inputs of the oscilloscope here that we can use to actually connect to our circuit or whatever device we're trying to take measurements from. Some of the ones that you'll find in the lab look either like this, where we have a test lead or probe that has a little alligator clip on it, or you'll find the other ones that have 2 much smaller pushpin style clips on them. These function almost exactly the same. They just have a few different features that might make them useful for different types of circuits. For instance, this type of probe is much better at high precision measuring. So if you have a very tiny little wire that you're trying to attach to and measure a voltage over time on that wire, you can just pull back the head of this probe and you'll see a tiny little clip that you can slip over whichever wire you would like. And then the other end always has to be grounded, because for any measurement to be accurately taken, your sensor needs to have both the actual test point that you're testing at, which is going to be this lead, and then a ground. That way, the ground for your oscilloscope is the same as the ground for the actual circuit that you're testing. So, for instance, if I built on a breadboard a simple circuit that had one resistor that was being powered by a power supply with a 5-volt input and then a ground connection, I would connect the ground clip of this test lead right here to the same ground that I'm connecting on my power supply. Or if I'm using these, the same principle applies. This red lead is our positive voltage test probe, and the black lead over here is our negative or ground. Now, how do we actually connect these to our unit? Well, each one of them has this style of connector on it. This is called a BNC, the letters BNC, a BNC connector. And this, you might have seen these in the function generator introduction video. It has a little head on it that screws left or right, has a thumb screw attachment to it, so it's very easy for us to move. And then it has two little divots in it that we slip over the two little notches that are on the plug on the oscilloscope itself. So we slip these over those notches. It sometimes takes a little bit of wiggling around to get it to push in all the way. And then, while still pushing in just a little bit, we turn to the right until the connector stops turning. You'll feel it kind of snap into place. And that way, we know that our lead connector is locked in. Now, these two leads are actually used as an input for our oscilloscope. And I can kind of play around with this to just show you that it is actually measuring something just by maybe touching the positive lead on the oscilloscope with my finger. And this is measuring some very small electrostatic voltage that's on my skin. So now let's see how we can actually use this to measure various different input signals. So to most effectively explain to you how we can use an oscilloscope for circuit analysis, what I've done is I've taken a function generator that's currently off screen and I set it to produce a sort of mystery signal. It has a given frequency and amplitude that I'm not going to tell you, but I'll show you how we can figure out exactly what those values are using our oscilloscope. Before we get started at that, let's take a look at what we see the moment we turn on the oscilloscope. First of all, we see one button here lit that has the number 1 on it, and it also has a designated color, this yellow, that also corresponds to the yellow number 1 down here. That is the channel 1 input. So since this yellow button is the only one that's lit right now, that means that the only input signal that is being plotted on here is channel 1, is whatever's connected to this lead right here, which is nothing at the moment, which makes sense. That's why we're not seeing any signal at all, except for maybe a little bit of noise on the display. These other buttons, if you don't actually have an input connected to each one of these channels, then I suggest leaving them off. If they come on by default whenever you turn on the machine, it might look something like this. You'll see another signal being plotted that is also just a baseline, no actual signal. So we can just press those buttons to turn them off. Sometimes it might show you, it might take 2 button presses to hide this extra settings menu, but that's fine. If you have to press it twice to get rid of that backlit number 2 there, then that works. So now let's actually take a look at some of our knobs on the machine. We have a couple of multi-purpose knobs up here labeled multi-purpose A and multi-purpose B. We have a section over here called the wave inspector. We have a horizontal position section. We have a trigger section, and we have a vertical section. Some of these are pretty self-explanatory. The horizontal and vertical sections allow you to move or scale your signal horizontally or vertically by using the corresponding knobs. The trigger level we'll explain a little bit more in a moment. The wave inspector allows you to place cursors on different points in your plot and then measure specific voltages at different points in the wave, which we will again go through in a moment here. But for now, let's get started by connecting our oscilloscope leads, these two, to the 2 function generator leads that I have, which look exactly the same. So I can match positive to positive, like so, and ground to ground. And you can see how connecting the ground signal there actually cleaned up our plot a lot. The moment that I touched the 2 positive leads together, we already started to see some kind of data, but it was kind of flickering, coming in and out. which is a very good diagnostic tool. If you're trying to plot a signal from a circuit and you find that your signal is kind of flickering, the very first thing you should check is to make sure that your ground connection is good. But now, looking at this data, we can kind of make out an actual sinusoidal wave in there. It does look like something periodic is occurring, but it takes up the entire screen and there's so much going on that we can't really tell what we're looking at. What we could do is, on channel 1, to adjust the vertical scale, I can turn this knob down a little bit, and you can see that it shrunk the amplitude of the wave, or rather expanded the plot to cover the entire wave and then some more space. I could even zoom into it like this by turning the other way, but this looks good right about here. Typically, whenever you're plotting a wave, you want to make sure that your wave fills most of the vertical space on your screen, but then whenever we plot the horizontal scale, we want to make sure that we only see 2 to 3 full, complete waves. That's your baseline, and then you can adjust from there as you need. So to actually get those 2 to 3 full waves, we need to also kind of zoom in on our wave, because currently we see a whole bunch of repeating patterns here, if we can even make that out in all of this noise. So on the horizontal scale knob right over here, I can also zoom in on that one, and you can start to see our actual sinusoid come into focus. So as I said, we're going for 2 to 3 complete waves here. And remember that a wave is from one peak to the next, or one zero crossing to the next. So this is one wave, and that is 2. This is perfect. So now we can see a very clean image of what our function generator is putting out. But now, how do we actually figure out what the amplitude and the frequency are? Well, this oscilloscope makes that very easy as well. In the Wave Inspector section right over here, let's try clicking on Measure. And immediately you should see this measurement toolbar open up on the bottom. We can click on Add Measurement by pressing this button that's right underneath there. Remember, these are not touchscreens, so you will have to use the buttons around the screen instead. We'll click on Add Measurement, and now we need to specify what type of measurement. Usually in this panel, if we had a bunch of different channels enabled, we would have the option to add measurements from our different sources. But since we only have the one connected, we can specify source A, source 1, my bad. And now we need to give a measurement type, which is a snapshot, because we only want to measure at a given moment in time. And now we can actually specify, whenever we click on that second button over here, what we are actually measuring. Right away, we see up at near the top of this menu is frequency. So to select that, I'm going to use this multi-purpose knob B. We know that's the correct knob because inside of this measurement submenu, it's labeled with that orange B icon. So I can use this to select exactly which item I want to measure. And once I have that selected, I can click on OK, add measurement here. And then, to close out of all of the menus, we can press the menu off button down in the bottom right here, right by our channel 1 input. And you can see right here in our little table of measurements on the bottom, we now have frequency. And the value that's being measured is about, our average value is over here, 284.3 K, so 284.3 kilohertz. I won't tell you yet if that's accurate. Let's first also plot the amplitude, and then we can compare with what we see on the function generator. So to plot the amplitude, this part can sometimes get a little bit finicky, because we now have to make note of some specifications of the actual machine. The input terminal here has a little label over it that has a bunch of different jargon, or a bunch of data that, for the most part, we won't need to know all that much. But we can see at the very start it says 1 M and then the omega symbol. That's 1 mega ohm. What that means is that this termination is rated at 1 mega ohm resistance. Meanwhile, our function generator, I'll go ahead and give this away, that one also has a little termination resistance on the bottom near the outputs, and it says 50 ohms. That mismatch can sometimes cause your amplitude measurements to be kind of completely out of whack. We'll play around with a few settings where I can show you how we can fix that. In many of our labs, we have little BNC terminators. A terminator is just something that converts one resistance to another resistance, basically matching those resistances so that we can get that complete, accurate measurement without actually having to play around with our settings as much. But at the moment, I'm just going to show you how to make do with what we already have built into this oscilloscope. So, to measure amplitude, we're going to go back to Add Measurement, which might still be open. If it isn't, then you can just click on this Measure button up here, and you'll see our measurement toolbar. Then we can go to Add Measurement, and now let's take our multi-purpose knob B and scroll all the way down to the next page where we see amplitude. In class, I mentioned that in electrical and computer engineering, it's often more useful to us to measure peak-to-peak amplitudes rather than just amplitudes. And for that, we can also just measure the peak-to-peak here. But notice these little helpful graphics that the oscilloscope is giving us, where the peak-to-peak even takes the actual noise in our signal whenever it's considering what the peak of our plot is. So in our case, when we have a pretty clean sinusoid like the one we just saw, we don't really have to worry about it that much. A peak-to-peak measurement should be perfectly fine. But if your measurement is a little bit noisy, then you might want to stick with the amplitude measurement, because you can see in that plot that it kind of eliminates some of that noise. It takes a more average high measurement. This is also better for reading digital logic signals like square waves. So I can go ahead and click on Add Measurement with my peak-to-peak value selected, like so. And now again, press the Menu Off button down here to close out of this menu, and you'll see that my peak-to-peak voltage is being measured at about 6.66, 6.67 volts. I can tell you right away that that's not quite accurate. That is not what the function generator is sending out, but that's because of our connection mismatch right here. This one is 1 mega ohm, while the function generator is 50 ohms. If you're just measuring a signal directly off of a breadboard, this might not be an issue. You might not have to play around with these settings at all. But in case your voltage doesn't look quite right, your amplitude voltage, you might want to try messing around with this and see if it sort of clears up those issues. So what we can do to modify the settings on our oscilloscope's inputs is to click on that input button, our channel 1 here, the same one that we would use to turn our channel on and off. And in fact, if I do press it again, it turns off that input. But we don't want to turn it off, we want to just open up this menu at the bottom. So you can see we have a couple of different options here. We have an AC or DC coupling. The primary difference between those two is that when you're looking at an AC coupled signal, it ignores a DC offset, which we went over in class. When you're looking at a DC coupling, it doesn't ignore that offset. It actually plots it on this wave. So if this wave had a 5-volt offset, the entire wave would be shifted up by 5 volts. Now, what we are actually concerned with to match the termination resistance that we were talking about is the termination section down here. And you can see that the default option is 1 mega ohm, whereas the other option that we're given is 50 ohms. Let's try switching those just by pressing this button down here. And immediately you can see our amplitude changes and our peak-to-peak voltage changes. Now it measures about 3.26, 3.27 volts, which is much, much more accurate for what the function generator is putting out. Now that we have those two measurements, I can switch over here to the function generator and show you what our mystery wave is. It was 284.31 kilohertz and a 3.2 volt peak-to-peak amplitude, whereas what we measured is a 284.3 kilohertz frequency and a 3.25 volt peak-to-peak amplitude. So both of these are just off by maybe 1 decimal place, which is honestly not bad at all. There are a bunch of different ways, more advanced techniques for getting a higher resolution or a higher accuracy measurement, but for almost all of our purposes, this will do just fine. So what we can do to modify the settings on our oscilloscope's inputs is to click on that input button, our channel 1 here, the same one that we would use to turn our channel on and off. And in fact, if I do press it again, it turns off that input. But we don't want to turn it off, we want to just open up this menu at the bottom. So you can see we have a couple of different options here. We have an AC or DC coupling. The primary difference between those two is that when you're looking at an AC coupled signal, it ignores a DC offset, which we went over in class. When you're looking at a DC coupling, it doesn't ignore that offset, it actually plots it on this wave. So if this wave had a 5-volt offset, the entire wave would be shifted up by 5 volts. Now, what we are actually concerned with to match the termination resistance that we were talking about is the termination section down here. And you can see that the default option is 1 mega ohm, whereas the other option that we're given is 50 ohms. Let's try switching those just by pressing this button down here. And immediately you can see our amplitude changes and our peak-to-peak voltage changes. Now it measures about 3.26, 3.27 volts, which is much, much more accurate for what the function generator is putting out. Now that we have those two measurements, I can switch over here to the function generator and show you what our mystery wave is. It was 284.31 kilohertz and a 3.2 volt peak-to-peak amplitude, whereas what we measured is a 284.3 kilohertz frequency and a 3.25 volt peak-to-peak amplitude. So both of these are just off by maybe 1 decimal place, which is honestly not bad at all. There are a bunch of different ways, more advanced techniques for getting a higher resolution or a higher accuracy measurement, but for almost all of our purposes, this will do just fine. There are a few more things that I want to show you using the oscilloscope. One is, suppose you just turn on your oscilloscope and plug in your inputs, and you see something that maybe looks like this. Is there a quick way to make it so that the oscilloscope sort of intelligently tries to adjust your vertical and horizontal scales automatically? Well, yes, there is actually. There's this auto set button up in the top center of our configuration panel. We can press on auto set, and our oscilloscope will do its best to follow the same principles that we use when trying to set our vertical and horizontal scale. So we can see that it encapsulated about maybe 4 or 5 different horizontal wavelengths, and then it tried to fill up the screen for the most part with the wave as well. And this is great. This honestly solves most of our problems whenever we're trying to very quickly plot a signal. And for the most part, you might not even have to use the horizontal and vertical settings at all. But there are still some ways that you can maybe zoom in on the parts of the wave that you care about by adjusting your scale. So I can, for instance, if I wanted to see more detail of what's going on at the top of a wave, I could zoom in, and then I can zoom in on both axes, and then I can shift the position of my wave using these tiny little knobs here. This I can use to shift the entire wave upwards to show you more accurately what that's doing here. I'll just auto set again and show you what's going on whenever I play with those knobs. I can use this knob to shift the entire wave vertically, which you'll see its x-axis on the left-hand side, this little 1 icon over here, that little cursor moving up and down. And then I can also shift the horizontal position using this knob. So I can use that to zoom in on different areas. But for now, the auto set wave that is plotted for us looks fantastic, so I'll just leave it alone. Now, suppose we want to get more details about what exactly the voltage or some other measurement is at exactly 1 point on our waveform. Well, we can do that too. Let's press menu off to get rid of this auto set menu over here. And now we can press the cursors button up here, which I will press and you'll see it turn on. And now you'll see 2 vertical lines appear. There's an A cursor and a B cursor, one right here, one right there. And we can move these with our multi-purpose knobs A and B, because we see those cursors each have that orange symbol right over top, just like our knobs do. So if I turn this knob, you'll see cursor A move. So if I wanted to measure the precise voltage at maybe 1/3 of the waveform, right about here, you can see where my cursor is by that little intersection line that's plotted for us. I'll move my cursor where I want it, and then up in this table up here, we can see that it's measuring about 0.5 volts, or roughly 500 millivolts on average, or maybe 480. So either 0.5 or 0.48 volts. And that's incredibly useful for us. We can even see what the difference in voltage is between 2 points. Like, what if I wanted to know what the difference in voltage is between this high point up here, that crest, and this low point down here? This is sort of a roundabout way of measuring our peak-to-peak voltage. Well, I'll move my cursor A to the crest of that wave, and then move cursor B over to the trough, or the lowest point of the same wave. And we can see that it gives us a delta value. Right here, it says that it's roughly 3.06 volts. That delta means change. That means the change in voltage between cursors A and B. And you can sort of, sort of see that delta changing as we move our cursors around. So the difference between that high point and maybe about halfway through this wave, it's around 0.76 volts, or 760 millivolts. So that feature is incredibly useful for us. Now there's one more thing that I want to show you. Suppose you do have a lot of this weird noise, or your wave is moving around a lot, or you see those flickers or reflections that are making it really difficult to actually get a good measurement off of your oscilloscope. The reason for this, as I mentioned, is that the oscilloscope is trying to take a bunch of data from a long period of time and then overlay it on top of each other to make one comprehensive image. And the reason it's struggling to do that is because it doesn't know where the start of a wave is. It's having a hard time figuring out where the beginning of a wave is and where the end is. So what we can do about this is adjust our trigger level. The trigger level basically is the voltage at which the oscilloscope says, oh, this is the beginning of my wave. And the best place in a sinusoid for that is typically around 50%, halfway between the highest and lowest point. So we can select our trigger level by pressing the menu button here, or just by starting to turn the knob. And you can see that, or hold on, let me figure out where it was. Okay, so that's why I wasn't able to find it, and that's also why our plot looked as weird as it did. The trigger level was way up above, outside the actual bounds of the plot, where, as I said, the best place to put it is somewhere in the middle. So if you turn this knob counterclockwise, it'll come back down. You can see this horizontal yellow line scrolling downwards, and as it gets closer to the center, it appears to stabilize. And this gives us a very, very clean measurement. So that's how we can fix that.